So in this section, we are going to look at the electric motor system reliability. A system is said to be reliable when it can deliver what it is intended to deliver. That is, it can function as at when it is needed, as it is intended for it to function. Such a system is said to be reliable. Okay, it's just like the reliability ordinarily that you know. Somebody is reliable when he could deliver on his promises or what is expected of him. So it is too with our assets. Okay, an asset is reliable when it can deliver what it is installed for or designed for to deliver, and it will be able to deliver that designed or expected capacity as at when it is actually needed of it to deliver. So in the case of our electric motor system, it can deliver on the reason why it was installed in the first place, when it is actually needed for it to deliver on that particular reason. So in that case, we can say the electric motor system is reliable. Okay, that is the ability to deliver as at when it is needed. Okay, what it is expected of it to deliver. Okay, so that is the reliability of the electric motor system. But as we will see later, there are various components in this electric motor system. So one of the mistakes that we often do in asset management is that we look at these components in isolation. Okay, we try to improve the reliability of each of these components in isolation, and doing that means that we fail to realize that these components, they are in series, which means that the reliability of any of the components in that series will affect the reliability of the entire system. How do I mean when I say the reliability of a component? So if you look at the right of your screen now, you will see the electric motor system ranging from the power input, okay, input into the system, to the feeders, to your electric motor, the circuit breakers in line with your electric motors, the contactor, and also the control circuitry, and of course the electric motor itself. So you will see that the reliability of all of these components, including the cabling, the feeder lines, okay, the reliability of all of these components, the electric motor, the feeder lines, the contactor, and the circuit breaker, and if you have isolator switches on them, all of these, and the control circuitry, all of this will affect the reliability of the entire system. So when you are looking at improving the reliability of the electric motor system, you have to look at it holistically, okay, with a view to improving the reliability of each of these components in the system, and as such improve the reliability of the entire system. And if you also look at it, also to be included is the load that will be driven by the electric motor, as you can see on the right of your screen, on the left of your screen, I mean to say. If you look at this load here, which is a pump, okay, you will notice that what we actually expected in our process from the electric motor system will be delivered by the pump. So if the pump's reliability is 40, remember it's in series with the motor, which will be in series with all of these components. Okay, so the reliability of the pump itself will also affect the reliability of the entire system. Remember, reliability is the ability to deliver what is expected of the system as at when we need it to actually deliver on such expectations. Okay, so the mechanical parts, the load that is driven, if it is fan, if it is compressor, or as in this case now, if it is the pump, the reliability of the pump also affects the reliability of the system. And of course, the reliability of this coupling and the pipings, okay, all of these will affect the reliability of the system. So when we are looking at the reliability of the electric motor system, we put into consideration every component in the electric motor system. Okay, so before we go into improving the reliability of each of these components, let us first appreciate how the major components, okay, remember we termed it the electric motor system. So in this case, we are focusing on the electric motor, okay. So let us see how the electric motor functions, because the understanding of how the principle guiding the functioning of the electric motor will help us to be able to discern when issues are developing. Okay, so let us look at the basics of electric motors operation. We know that electric motors have two major component parts. Okay, it has the rotor and the stator. So each of these stator, as you can see, they have windings in them. They have three-phase winding that are wound into three-phase belts. Okay, so these three-phase belts, they are separated by 120 electrical degree. Remember, because in the course of this program, you will come to see how that affects what we are expecting. Okay, because the input power, they also have that kind of phase relationship separated by each of the phase separated by 120 electrical degrees. So that is what we see here in the electric motor. Okay, so the terminals, the lead outs from these windings, they are connected to these terminal blocks. So we have two lead outs from each of these phase belts, okay, on the terminal block. So on the terminal block, we have 6 lead outs or 6 terminals, okay, 2 from each of these phase belts. So on the terminal here, we can either start, as we have discussed in some of our other trainings, we can either start the motor or delta the motor. You can check out our earlier training on electric motor or electric motor testing, okay, or the use of digital multimeter in testing electric motor. So that is the stator. Then the rotor, as you can see, we have windings in them too. Okay, these are conducting bars, as you can see on the rotor, aluminum bars. Okay, we have several of them, as you can see, and then this bar is shorted by this end ring. Are we getting it? It's shorted by this end ring. So that is what you are seeing here now. Okay, so these are the aluminum bars, okay, and then this is the end ring, as you can see on the screen. Okay, so these are the windings. These bars, they are the windings on the rotor. Okay, so let us see how it affects the operations of the electric motor. Now remember that when you connect the electric motor to your three-phase signal, as you can see here, it means that you are sending voltage that are displaced by 120 electrical degree from one another. That is the 3 phases into this stator winding. So that will end up magnetizing this stator winding. So that stator winding, the magnetic field that will be created will be rotating in the direction of the rotation of that electrical the voltage signal, okay, that is coming into the electric motor system via, that is the electric motor via the terminal block. That is the sequence Okay, if it is red, yellow, blue, it will be going in that sequence displaced by 120 electrical degree. So the field that will be generated here, okay, will also exhibit that sequence. Are we getting it? So that changing magnetic field as it's changing, because the terminal is directly connected to your line now. So as that magnetic field is changing, what will happen, since this one is coupled inside, it will now induce current. That is, current will now start to flow in these conducting bars. Remember that current carrying conductors have magnetic fields generated around them, which means magnetic field will be generated around this rotor. Okay, so that magnetic field on the rotor will now interact with the magnetic field on the stator. Okay, that is what we call the magnetic flux linkage, or linkage flux. Okay, and the resultant effect will be that tangential force will now be created on this rotor, and the rotor will start turning, okay, in the direction of that phase sequence, okay, as we have discussed before. So the electric motor will start turning. So anything that could affect the magnetic field that is created by either the stator or the rotor will definitely affect the integrity or the reliability of the electric motor itself, okay, which will in turn affect the reliability of the electric motor system. So what other things could actually affect the operations of the electric motor? Let us see other components of the electric motor and what they do in the electric motor and how they can affect the reliability of the electric motor itself. Okay, so when you look at this is the rotor that we have discussed earlier. Okay, then this is the stator windings that we discussed earlier. Of course, anything that will affect the reliability of this will affect the reliability of the system. But aside these two, if you look, you will see the frame. Okay, and if you look at the frame, you will see some fin-like structures that look like fins on the body of the frame. Okay, we'll come to this later and the importance of it. Then if you also look, you will see that we have a fan that is attached to the non-drive end of the motor. This end is the drive end. Okay, this is the fan attached to the non-drive end, and this is the fan shroud or cover. Are we getting it? So as the rotor is turning, since the fan is attached to one end of the rotor, okay, this generates air, okay, that is blown through this motor frame. So the function of this fin-like structure is to retain the air on the frame as much as possible, so as to enable effective conduction of heat, okay, that will be carried from the winding during operation to the frame of the electric motor, away from the electric motor. So all of this helps to effectively cool the electric motor. So once it is plugged, maybe by dirt covers it up, it will affect the reliability of the electric motor itself. Are we getting it? So we want to maintain it clean at all times, free of dirt. All of this, so that the channel will be open for breeze that will be generated by the fan to go through to effectively cool the electric motor. So other components are the bearings. Okay, so these bearings, as we'll see later, they can also affect the reliability of the electric motor, because this bearing, they are meant to hold this rotor in position, okay, to be in the center line of the stator. Are we getting it? So if peradventure one of them is not properly aligned, maybe because of worn out housing, you'll see that this rotor can rub on the stator, which can affect the integrity of the machine. Okay, so we'll see all of this later and how it can affect the driven load itself. Are we getting it? So the reliability of this seemingly unimportant component is also very, very important to the reliability of the entire electric motor system. So we want to take note of this also. Okay. Now we are still on the electric motor system reliability. Remember, we segmented the electric motor system into two. Are we getting it? Remember, we considered the load, that the reliability of the load will also affect the reliability of the electric motor system, as we discussed earlier. Okay, now we want to, for us to ensure the reliability of the system, we ensure the reliability of the electrical parts of the system. Okay, that is the reliability of the electrical system and also the mechanical system. So like we said earlier, as you can see on the right of your screen, that is the electrical system, from the input power through those electrical components, circuit breaker, contactors, the control circuitry, then to your electric motors. Okay, so everything on the power line and on the control circuitry. Okay, the reliability of all of them will affect the reliability of the electric motor system. So we are going to consider that. And then we are also going to consider the reliability of the mechanical part, that is the driven load of the electric motor system. Okay, so here we have a pump. Could be a pump, could be a fan, and it could be compressors. Okay, whatever that is driven by the electric motor. Remember, what we needed from the system into our process will be delivered by that attached load to the electric motor system. Okay, so we are going to look at how we can ensure the reliability of this and thus ensure the reliability of the entire system. So, but first, let us look at the electrical system's reliability. So when we say electrical system, remember we are talking of everything from input power to our electric motor through the control circuitry. Okay, so we are going to look at 6 zones, that is the electric motor, 6 fault zones of electric motors. Okay, so we are going to look at the power quality, that is the quality of the electric power that is delivered to this bus, okay, either from your utility, either from the utility in your system, okay, in your facility, or external utility. So we are going to look at that. Okay, then we are also going to look at the insulation fault zone. The insulation fault zone that has to do with the insulation of the windings, either to ground or between phases in the electric motor itself. Are we getting it? So we know that that can affect the reliability or the integrity of the electric motor system, or the electric motor, and thus the electric motor system. So we are going to also look at the rotor fault zone. Remember those components that we outlined earlier, how they can rotor, okay, how they can affect the electric motor system operations. Okay, so we are also going to look at that and what we need to look at when we are testing this fault zone. Then the power circuit itself. But when we say the power circuit, what we are actually talking about is the input feeder line, everything on the feeder line to the electric and the motor winding and to the motor winding. Okay? So all of this forms the power circuit. Feeder line, the components of feeder line, circuit breaker, contactors, all of these they are going to. Then the air gap, which is the space between the rotor when it is coupled, when the electric motor is coupled, the space between the rotor and the stator. So that forms the air gap. Okay? That is the air gap, how it affects the ability of the system. So then the stator itself. In this case, we are going to look at the windings, okay? How it affects the electrical motor systems. Okay. So let us dive straight to the first one now, which is the power quality. So we want to see what power quality really means. So as you can see on your screen, power quality means the quality of the voltage or the power that is supplied to your system. Okay, that is the quality of the power that is present here on this bus in your MCC. Are we getting it? So now when we say power quality, remember we expect that the power that will be supplied to this bus must be of a definite magnitude. Okay, and then their phase difference, like we said, identified earlier, must also be 120 electrical degrees, since we have deposited those coils on the stator, okay, at that separations to 120 electrical degrees. And then we also expect that input power to be at a particular frequency. Are we getting it? So that is the quality that we are talking about, which means the normal voltage as indicated on the nameplate of your electric motor. So that should be what will supply to the motor system. And then of course, what we are supplying to the electric motor system must be a pure sine wave. Anything that is outside a pure sine wave means that the quality of that power has been distorted. So the how, we will see that as we go along. So now, what are the various power quality issues that can affect the quality of the power that we are actually sending to our electric power system? So they could be actually divided into two broad category. Okay, we have the steady state variations or event, and those transient or temporary events. So on the steady state event, we see the voltage unbalance. We'll see how it will affect our system later. We'll see the harmonics, what they are and how they affect the system. Then flickers, voltage flickers, notching, noise. Then on the transient event, we have transients, okay? That is temporary events. Voltage sag, voltage swell, we have interruptions and DC offset. So we are going to see how all of these actually will affect the reliability of the entire system. Okay, that is the motor system. So let's look at the voltage unbalance. Like we said earlier, the three phase of the power supply must be at the same level, the same magnitude. So if the supply is indicated 415, okay, it means that the phase to phase must be 415. As you can see here, the red phase, the blue phase, and the yellow phase, they must be at the same magnitude. Are we getting it? Then the phase difference also, okay, must be 120 degree apart. Okay, So that is what is supposed to be maintained for our voltage to be balanced. Are you getting it? Then the voltage will not be balanced if any of these phase is higher than the others, as we can see on this other voltage signal, okay, or waveform on the right of your screen. So if you look at it, you'll see that the three phases, they are not balanced, they are not equal. Are we getting it? So once they are not equal like this, it affects the integrity of the entire system, and most especially the electric motor itself. So if you look at the top right of your screen, you will see what you could observe when you use a power quality analyzer on your system. Okay, so as you can see, this is the various voltage levels of the three phases, and as you can see clearly, they are not of the same magnitude. Okay, then the frequency is 50 Hz, which is what is expected if the system is a 50 Hz system. Okay, then look at the phase angle. If this is 0, especially this one is supposed to be 120. If you look at it, we are having 118, which means that it is out of phase by 2 degrees. Then the third, 120 plus 120, we are supposed to have 240. And here we are having 233. Okay, which means that with this reading, we are having power quality issues. Now, what is the level of imbalance in this system? So to calculate the level of imbalance in this system, as you can see, we have the first phase, we have 236.4 volts. Then the second phase, we have 234.5. Then the third, we have 239.3 volts. So we'll take the average of this, okay, which means that we are going to add all of them together and divide by 3. When we do that, we will get an average of 236.7. 236.7 becomes our average voltage. So we'll now look at the difference between each of these phases and the average. Okay, so if we look at the difference, we'll see that on phase 1, we have 0.3 volts. Phase 2, we have 2.2 volts, and phase 3, we have 2.6 volts. Okay, so now the highest deviation from the average is at 2.6 volts. So our unbalance will be that highest deviation, 2.6, divided by the average that we calculated earlier, which is 236.7, and that will give us 0.011, which is 1.1%. So the voltage unbalance on this system is 1.1%. So it actually depends on the tolerance of the system. Of course, this will definitely have an effect, as we will see later, 1.1%. Okay, but the allowable range is between 0.5 and 2.5%. Anything above 2.5% is unacceptable, because the effect on the electric motor itself will be very, very catastrophic, and it can lead to the system downtime, okay, or frequent failure, so to say. We'll see how this will also affect the electric motor itself, and even the system as we go along. So now look at how the voltage unbalance, okay, this graph shows how the voltage unbalance will affect the temperature rise of the electric motor itself. Okay, so as you can see, a 1% unbalance can cause 2% temperature rise. Are we getting it? So a 2% unbalance can cause 8% temperature rise. 3% unbalance can cause 18% temperature rise. Okay, because that unbalance has a way of an unbalance has a way of affecting the current that flows through the windings at the end of the day. An unbalance of 1% can cause or can result to an unbalance of between 6 to 10% in the amount of current. That is an increase in the amount of current that flows through the windings of between 6 and 10%. So that is huge. Okay, so just imagine you have an unbalance of say 4 volts. If you have an unbalance of 4 and one is causing an increase in the amount of current of 10%, that is automatically a 40% increase of the amount of current that is flowing through the windings. And as you well know, the amount of current that flows through the winding affects the amount of heat that is dissipated in each of these windings. From the formula power loss equal to I square R. It is exponential, the effect. Okay, so you see that the heating effect of that small variation or small unbalance is huge as the difference is going up. So voltage unbalance is an undesirable situation in the operation of electric motor. So usually it is recommended that at the input stage from your utility, the voltage unbalance should not be more than between 1 and 2%. Okay, should not be more than 1%. Are we getting it? And because of all of these effects that we are seeing on the screen. So voltage unbalance is an undesirable event. So you check the unbalance at the input, and then that is at the input into the motor system. That is the input into your circuit breaker or into your fuse. Okay, into your fuses at the MCC. And then the input into your motor at the terminal block of the electric motor. So you want to check it to see that they are balanced at all times. Okay, then as you have it here, you also can check whether it is balanced here at this point, whether it is balanced here, okay, and whether it is balanced here, so that you'll be able to zero in on where particularly the unbalance is coming from. If it is not coming from the power supply, it can come from these lines, as we will see later, okay, because of resistance build-up. Are we getting it? So it is very important for us to maintain balanced voltage to our electric motor. So next, we are going to look at under voltage and over voltage. When we say under voltage, okay, what we mean is that the voltage is less than the normal voltage level that we expect in our system. So if it is less than say 90%, okay, of what we expect in our system for about say more than 1 minute, that is under voltage. And under voltage, remember, the electric motor will exert a definite level of power in our system. Are we getting it? So since P is equal to IV, P is constant, V has gone down. What will then happen to I? I will definitely go up to balance up the differences so that we'll have that constant power, okay, on the system. So if I goes up, what will then happen to the heat that is dissipated in the winding? Of course, remember the effect is exponential, okay, because the heat that is dissipated is given by I square arrow. Okay, so that is why under voltage is not good for our system, because it will increase the heating level of the electric motor, reduce the insulation capability, destroy the electric motor insulation, cause winding burnout. Are we getting it? Especially if the under voltage is sustained for a very long time, or it is repeated over a period of time. Okay, so the next that we are going to look at is over voltage. So when we say over voltage, that is, the voltage is more than what is expected in our system. Okay, say about 110% and above. And if it stays for more than 1 minute, okay, that becomes an over voltage. So such over voltage is also not good for our system. Are we getting it? It's not good for our system because it has the tendency of increasing, apart from increasing the losses also. Okay, you see that the motor will tend to want to run at a higher speed because of that increased voltage level, which may not be good for the end products in our system. Okay, so over voltage, again, apart from that too, it also has the effect of stressing the insulation of the electric motor system. Remember, these insulations, they are designed to withstand a level of voltage. Okay, that determines the breakdown capability of this insulation. So you're repeatedly stressing them with something that is beyond what is normal will eventually make them to give way, especially at the weakest point on the insulation. So over voltage too, we need to protect our system against over voltage. So we also have other power quality issues that can affect the reliability of our electric motor system, and that is sags and swell. Okay, sag, like under voltage, is when we have about that 90% power unit, okay, into our system, but this time at a lesser time. It has a very short duration, that is from 0.5, that is half cycle of the voltage signal, to about 1 minute. Okay, then swell too, like over voltage, 110% and above of the standard power unit in our system. Are we getting it? But this time it's for a lesser time. What that means is that if that over voltage is experienced, okay, for between half a cycle to about 1 minute, that becomes a swell. Are we getting it? So sags and swell, like under voltage and over voltage, they are still not good for our system, okay? Because under voltage, that repeated increase uh, current flow over, that is sag now, repeated increase current flow, okay, stresses the conductor and the insulation. Then over voltage, that is swell now, also has the effect of increasing the stress. Remember the pressure on the insulation of apart from the increased speed that it will eventually cause on the system. So there are some of the power quality issues or signal or abnormalities that would need to guide or protect our system against. Then we have flickers, that is the voltage is fluctuating randomly or irregularly. Are we getting it? It's like when you flickers, you notice it in bulbs. Maybe if you have fluctuations, frequent fluctuations on the voltage signal, those incandescent light, you see it going up and down, as you can see on your screen on that incandescent light right now. Okay, it will be going up and down. That is called flickering. Are we getting it? So flickering too is not good for our system. Okay, it's not good for our system because like the sags, over voltage and the rest, they can cause shutdown. Depends on the protection you have on the system. Can cause shutdown, and at times it will take you a lot of time to start up the system again. Then if production is in process already, you see that those materials that have been prepared for the next stage of your production process may be wasted. Are we getting it? So these flickers too can also cause similar effects on the electric motor system. So we want to guide against this. So the next that we are going to look at is transients. Okay, transient, basically they are introduced by lightning. They usually appear as spikes in our voltage signal or waveform. You see that spike will overshoot the limit, okay, of they are usually very, very high. Remember, when lightning strikes, it creates electromagnetic field. Okay, that electromagnetic field that is created as the lightning is discharging into the earth induces voltage into our electrical system. These are the spikes. They are usually very, very high voltage. So if they are allowed into the system, okay, it has the effect of causing insulation breakdown or stressing the insulation repeatedly. It will eventually cause breakdown if your insulation is that strong enough. But in some cases, as it enters, that first entry can destroy the insulation of the components in your system. Okay, so we want to protect our system against such transients that may happen in the system. Okay, so we have discussed voltage swell before, and this one that we saw here, this is sag. Okay, this is the sag. It lasts for less than a minute. Are we getting it from half a second to about a minute? Then the swell, you see increased voltage that lasts for the same half a second to about a minute, as we discussed before. Then we have voltage interruptions, or we have interruptions. That is when there is a break in the voltage waveform or signal, okay, for more than 1 minute. That is called interruption. Are we getting it? So such interruptions too, they are not good for the operations of the electric motor system. Are we getting it? So all of this we need to protect against. Then variable frequencies. The frequency of the electric motor of the power supply have a way of affecting the speed, or it affects the speed of the electric motor itself. Okay, so when the frequency is fluctuating, that will cause fluctuation in the speed of the electric motor, that will eventually cause fluctuation in the rate of, that is the rotational speed of the driven equipment. So this driven equipment, if it is a pump, it means that at times it will deliver more than what is expected, and at times it will deliver less than what is expected. If it is compressor, the same thing too. Okay, and such variation we know is not good for our process, especially for sensitive process. Okay, so let us look a little bit in details the unbalance and the harmonics, as we said earlier. Okay, so we said it is balanced when the magnitude of all the phases at all the time they are equal. Are we getting it? It becomes unbalanced when they are not equal. Okay, as you can see on this diagram to the right. So we see that some of the phases, they are higher, okay, in magnitude. This is 100% the power unit. So if it is 415, what we have here is 415. If it is 220, what we have here is 220. Okay, so you see the fluctuation, some are less than that 220. So the voltage is unbalanced. Okay, so we'll see the reason why we need to protect our electric motor system against unbalance when they occur. So if you have equipment or instrument that you can use to look at the power quality in your system, so you have this kind of display on such equipment, okay, that is power quality analyzers or meters. Okay, so this is the one to the right is the phasor diagram, and to the left we have the information of what we have on the system. Okay, so you see the voltage levels. We have 236.4, we have another 234.5, and we have another 239.3. okay, so if you also look to the right, you will see the phasor diagram, and you see the phase angle. You see that they are not entirely in phase, and this is what is shown on the left of so the first one, if it is 0, you see that the second one is not 120, because we are having 118, and this third one is not 240, we are having 233. Okay, so you see that the phase difference is a little bit abnormal, it's not normal or as expected. Are we getting it? So let us look at how we can calculate the unbalance from this system. The unbalance, usually what we do is that we take the average, okay, of these 3 voltages, okay, and subtract each of them from that average value. Then we'll now use the highest deviation, okay, take the highest deviation and divide it by that our average. So what we have will become the unbalance that we have in the system. What we mean is that we'll add this to this and this, and if we do that, we have 200, and if we add this to this and this, we have that is 236.4 plus 234.5 plus 239.3. okay, when we add, we'll have and divide by 3, we'll have 236.7. 236.7, that becomes our average voltage. So this average voltage, when we take the difference Between 236.4, we have 0.3. Then difference with that is the average minus 234.5, we have 2.2. Okay, then the average, which is 236.7 minus 239.3, we have 2.6. Okay, so the highest is that's 2.6. Are we getting it? So the highest is that 2.6. That is the highest deviation. So we'll now take that 2.6 and divide by the 236.7, which is the average, and we'll have 0.011, which is about 1.1%. Okay, so the unbalance in this case is not much of an issue. Are we getting it? So unbalance between 0.5 to about 2.5%, they are a kind of acceptable. It depends on the tolerance that your establishment set or they agree on. Okay, so the unbalance that is more than 2 in some establishments, anything that is above 2 is unacceptable. You have to do everything possible to bring it back to that, down to below, far below 2. Are we getting it? Okay, so that is for the unbalance. And the unbalance, why it is very dangerous, can be shown in this diagram that you can see. Okay, this graph. So on this graph, you see the percentage of unbalance and the expected temperature rise. So usually an unbalance of 1 percent can create current unbalance of about between 6 to 10%. You can imagine that. So that will mean that the heat that will be lost, the dissipated heat or energy that will be lost from the system in the form of heat, okay, will increase by that amount, 6% and 10%. Are we getting it? So if that happens, we know that clearly that heating effect will affect the reliability of the electric motor itself and thus the system. So if you look at it, 1% voltage unbalance can result to about 2% temperature rise of the system. Then 2% voltage unbalance, 8% rise of the temperature of the motor system. Then 3% unbalance, you can see, are we getting it? You can see if say we have temperature rise from the ambience during normal operations, okay, say about 40 degrees Celsius. That is what we have. You can see that 2% voltage unbalance can cause a temperature rise of about 4 degrees Celsius. Just imagine that we have higher unbalance in the system. What will happen? You'll see that the temperature will increase, and that will affect the insulation integrity and subsequently cause failure in the insulation and cause a shorting of the turns and burnout of the windings. Are we getting it? So it is something that we must guide against in the electric motor system. So harmonics, you know, we said ideally what we expect to come into our system is sinusoidal, but in reality we do not have that. Okay, so what we have in reality is this kind of distorted waveform. Why is it distorted? It's because we have other voltage signals, okay, that are superimposed onto this fundamental signal that we expect to go into our system. So that is what you are seeing on the right. If this is the fundamental, these are harmonics, okay, 2 times the fundamental frequency, 3 times the fundamental frequency. So all of this superimposed onto this will now give us this distorted wave form. Okay, so this distorted waveform, remember the only usable one here is this. So all of this will go into our system to create problems. All these energies, they must be dissipated somehow, and they will be dissipated within the system. Okay, so we must guide against it. Okay, so we can see the effect, the distortion, that is the black waveform, which is what is so all of this superimposed into this fundamental waveform cause all of this distortion. So this is the kind of waveform that we will be seeing mostly in our system. Okay, so let us look at the effect of voltage variation on the motors. Okay, so if you look at the graph, you see that we have percentage variation as against percentage changes in the motor performance. So we are looking at a few performance parameters. Okay, the full load current, power factor, efficiency, starting current, and torque. Are we getting it? So you see, if there is no unbalance, you see that the motor will be operating at its equilibrium, maximum efficiency. Look at the efficiency curve. It is operating at the maximum efficiency. Are you getting it? Which means that the efficiency at this point is at the highest. Look to the left, you see drop in efficiency. Look to the right, you see drop in efficiency. Why are we experiencing all of this drop? Let us look. If we have under voltage, okay, of 5, 10, or 15%, how does it affect? You see the full load current increases as the under voltage is increasing, okay, and drops as we are experiencing no voltage variations, no voltage unbalance. Are we getting it? So as the voltage unbalance is increasing to the positive, you see too the full load current is also increasing. And once the full load current increases, that will increase the heat loss in the winding and reduce the efficiency. Okay, that is one of the reasons why we have reduced efficiency on the left and on the right of the equilibrium point. So how do we monitor this power quality to do what we need to do to correct or to remove these issues that are in our system? So we have the power quality analyzers. Okay, the power quality analyzer will help us to look at the power system, know what is actually happening in the power system, what kind of power quality issues that is plaguing our system or that are plaguing our system, and that will give us an idea as to what to do in order to make our power system to be more reliable, and thus our electric motor system to be more reliable. Okay, so this is the Fluke product. As you can see, this is the power quality analyzer that is connected to an electric motor supply circuit. Okay, so this will give us the voltage and current events over time. Okay, so if there are any issues, the probable cause of that particular issue on the system, from the analysis of what the event log will be able to ascertain or zero in on what the problem actually is. Okay, so this meter can help us to look at the current and voltage, the root mean square values, as we saw earlier in when we were looking at unbalanced voltage. Okay, it will also help us to look at the phase relationship. We also saw it earlier, whether the phase relationship between the three phases of our power system or our power supply is normal. Okay, even the current relationship, we also look at it. We also see it. Power factor and the frequency of operations, we'll see them. Then the active, reactive, and the apparent power. Okay, we'll see them so that we'll have an idea of the usable power and even what to do in order to correct the power factor in our system. The active energy, the reactive energy, and the apparent energy all will be clearly seen in the analyzer. Then the harmonic distortion, okay? We can remember, like we saw earlier, we saw that so many other voltage signal, okay, that are integer, that have frequencies that are integer multiple of the fundamental frequencies. They are superimposed into the fundamental waveform and thereby distorting it. So with this meter, this analyzer, we'll be able to carry out what is called a fast Fourier transformation, known as FFT. So with the fast Fourier transformation, we'll be able to separate all of these signals according to their frequencies of occurrence. Okay, so we'll see the contribution of each of these harmonics into the distortion in the process. So we'll see the harmonic spectrum and be able to know which of them is causing the problem in our system. So this is how the quality analyzer is connected to the system. Okay, so this now we can actually place this in two ways. We can place it at the input into our facility where power system interfaces with our facility. Are we getting it? So that we will know if what is entering the system is of the required quality. Then we can also have it connected or placed to our load, that is the electric motor load on the feeder line. So what this means that we can place it upstream of our circuit breaker. When we place it upstream of our circuit breaker, of course, we'll see everything that is happening within that feeder line, okay, on the system. So we have four current probe in most cases, but if you have a direct three-phase equipment or three-phase line, you connect the three current probe, okay, as shown on the diagram on the left. Then we have also three potential probe. It is usually four, one on the neutral. Are we getting it? So you have those three potential probe on each of the phases to give you the potential reading on the analyzer. So this is the current probe and these are the potential leads. Okay, so you see you having this for earth, neutral, line 1, line 2, line 3, also neutral, line 1, line 2, line 3. Okay, so that is what you are seeing on your screen now. Okay, that is what you are seeing on your screen now. These are the input of the current input, as you can see here, and these are the potential input, line 1, line 2, line 3, then neutral, as you can see. Okay, so these probes, you fix them here, 1, 2, 3. Then these probes, you fix them here, 1, 2, 3, okay, and neutral. So the probe that you have here and here, you must take them to line 1. Are we getting it? Then the probes that you have here, the potential at the current probe, must take them to line 2. Then here, the potential at the current probe, you take them to line 3. Then here, the potential at the current probe, you take them to the neutral connection. Okay, so you can actually set it and leave it and then for the equipment or the analyzer to collect information for you for over some time. Or you can look at what is happening in the system real time to know how the system is actually behaving as you are monitoring the system. Okay, so this is what the analyzer look like. So you see that you have the voltage and the phase information as we saw earlier, and the phasor diagram. So this is the waveform, current and voltage waveform. Okay, this current and voltage waveform, as you can see, to the untrained eye, it actually makes no sense. It looks confusing. Are we getting it? So remember, we are having this kind of waveform because we have harmonics in the system that distorted or that is distorting the normal waves sinusoidal waveform. What you are seeing here now is not sinusoidal. So to help us to have a good sense of what we are seeing, although we can determine the voltage levels and the current levels from what we are seeing at different times. Okay, so we'll know when we have the peak consumption or the highest current and voltage event. Are we getting it on the system, or the lowest? They are clearly visible, the dips and the heights, you understand? Or let me say the valleys and the highs on this graph. But to enable it make some sense to us, we can press the harmonic button on the analyzer. As you can see here, this is harmonics. Okay, if you press it, you have something like this. So you see that it has separated all those waveforms that is causing that distortion into their various frequency of occurrence. Okay, so as you can see here, we have the fundamental frequency, which is 1 times the frequency. Then the 2 times, there is no frequency. As you can see, there is no occurrence here, as you can see. Then we have at the 3 times, we have at the 5 times, 7 times. Okay, so if you look at the magnitude, you see that the magnitude, they are not so great. Are we getting it? The magnitude are not so great, and that is why we have this minimal unbalance. Okay, as you can see here, the unbalance is not too much. If we calculate it now, the meter itself can also give us the unbalance. Okay, so look at the total harmonic distortion on each of the phases. We have it 3.4, 2.1, and 1, which is okay, which is acceptable. Okay, you know, if you are looking at the input from your utility, it is advised or it's recommended that the total harmonic distortion should not be more than 8% at the point of input. Okay, if it is more than 8%, of course, you inform your utility to do whatever they need to do to reduce the distortion, harmonic distortion. So as you go into your system too, remember those nonlinear loads that we have in our system that helps us to improve the life. Okay, that helps us to improve our operations. They also have the effect of introducing such harmonics that will become problematic if we do not take care of them. Okay, so when such happens, we also see them in the system as we are monitoring, as we are moving away from the input point or the point of common coupling between your facility and the utility. So this gives us the beauty. Okay, remember these harmonics, these triplet harmonics, 3, 9, 15, 15, and 27, they are the most problematic harmonics. Okay, those remember these harmonics, we have those that are positive sequence. Okay, those positive sequence, they generate magnetic field, especially when they go into your electric motor, that are in the same sequence with the magnetic field generated in the electric motor unit. That is, they rotate in the same direction, simply put. So they will not affect it. While negative sequence, which are the even integer multiple, that is 2, 4, and the rest. Okay, what they do is that since they are negative, they act against the magnetic field that is created by the normal phase rotation of the voltage that you need to run your electric motor. So that will kind of affect the efficiency of the electric motor. But those triplets, zero sequence harmonics, they behave like single phase load. You remember, if you do not balance up the phases, okay, the load on each of the phases, what will happen? You see that you have current flowing on your neutral. Are we getting it? So if you have those triplets, they will tend to add up, since they will not cancel out, they will tend to add up on the neutral and cause neutral overheating. Okay, and also within the electric motor system also, they cause a lot of overheating if they go into the system and into your electric motor system, cause a lot of overheating in the electric motor system that will eventually affect the integrity of so the harmonics, we need to guide against, okay, those harmonics as they come into the system. Then, as you can see, also the transients can also be shown by this analyzer. So those transient events, okay, those voltage spikes that we have, maybe as a result of lightning or what have you, all of them will be clearly shown in the analyzer. So when it happens, and maybe if there are some failures that occur at that point, we will know clearly that that is precisely what caused that failure. Okay, and as we well know, all of this can cause insulation breakdown and shorting of phases or windings, and eventual destruction of our electric motor or the line supplying our electric motor. So there are a few solutions to power quality problems that we have. The most notable, which is the under voltage and the sags, that is voltage fluctuations, okay, all those voltage, unwanted voltage events. How can we guide against such, or protect our system against such voltage fluctuations? Are we getting it? Or unwanted voltage event. So the voltage regulator or the voltage stabilizer will help us, okay, because the voltage stabilizer will tend to regulate and make what we send to our electric motor to be steady. Are we getting it? So the input power from the bus will go to the stabilizer, and then the stabilizer will now be connected, or the voltage regulator will now be connected to the circuit breaker feeding our electric motor. Okay, so these are some of the voltage regulators that we have ordinarily. Okay, then electronic components or equipment, remember those transients, if they go into your electronic system, they will destroy all these components within the system. Okay, and you now have a different challenge altogether, in addition to installation failure that may be caused on the electric motor. So such suppressors, they are very good because they tend to clip the surge at the input, okay, and help us to protect our system downstream, even our electric motor. So noise too, okay, can be protected. That is, can be the problem of noise within the system can be solved by the use of line filters. Okay, even the problem of harmonics can be solved with the use of these isolation transformers. Are we getting it? So say this is the voltage signal coming into since they are electrically isolated, okay, they are only magnetically coupled. You see that only the usable voltage waveform will be active, and that will induce voltage into the secondary of the transformer, and that is what will now be sent to our load. So you see that what will be sent to our load will be very free from all of these harmonics. Are we getting it? So that is one way that we can actually solve that problem. Okay, so next we are going to look at the electric motor installation. Okay, so we have you can check out our training on installation resistance testing. Okay, we have that training also, so you can check that. So but the installation, what we are actually looking at is the stator windings. Are we getting it? So the insulation between each of these phases. Remember we said the windings, they are wound into 3-phase beds. Okay, so those phase beds, they are separated by lead rods. Just check out our training on insulation resistance testing on electric motor. So we test the insulation separating these phases, and then the insulation separating the phase and ground. So what we'll do is that we have the insulation tester, omega insulation resistance meter. Then we have one of the probe on the each of these phases. Okay, since you have it dated like this, it means that all of the windings, they are connected together. So if you have one probe here and one probe on the frame, that will give us the insulation between that is the body, that is the ground, and the windings. Okay, so if we remove those bars, we can test the insulation between the U phase, the V phase, and the W phase. Are we getting a U, V, V, W, and W, U? Okay, so usually we expect the insulation to be high. If we are looking at low voltage electric motor, 10 meg is okay. Okay, but if we are looking at medium and high voltage electric motor, 100 meg is okay. But even at the low voltage electric motor, we need something to be, we need the insulation resistance to be very high. The higher the insulation resistance, the better for us. Okay, so the insulation fault zone is another area that we need to look at, because a failing insulation will affect the reliability of the entire electric motor system. Okay, then we also want to look at the rotor fault zone. Remember, as we discussed earlier in this section, the rotor, the feed generated in the rotor, interacts with the feed generated in the stator. So anything that affects that feed, what will happen is that they affect that interaction. What happens is that the efficiency of the electric motor will be affected. Okay, so that is what we actually do here. Okay, we use the mega tester MTR105. Okay, the MTR105 can actually assist us in doing this, because we check the inductance, okay, the rotor influence, how the rotor changes in the rotor direction, position, I mean to say, affects the inductance of the stator winding. Are we getting it? So as we take that reading, as we rotate, we take the reading, we'll see the rotor influence on that inductance. Okay, so when there are problems, especially when residual flux or magnetic field in the rotor is more than what is normal, okay, we'll see it during that rotor influence test. So in doing that test, it's just to take this the selector switch to this inductance, capacitance, and resistance test selection. Okay, fix your probe appropriately at the top, and then you conduct the test on the electric motor. Okay, you can also do inductance unbalance test. Are you getting it? Although that will give you an idea of the stator winding, okay, resistance. That is tells you the integrity of the stator winding, okay, as we'll see much more later. So the next is the power circuit. The power circuit is also another fault zone. So like we said earlier, the power circuit is from the beginning of the feeder line to the termination on your electric motor. So anything that affects this power circuit will affect the reliability of the entire motor system. Okay, so what we do on the power circuit is that we do low resistance testing. We use the milliohm meter. Are we getting it? To test if there are resistance build up. We know that if there are resistance build up along any of these lines, what will happen is that it can cause voltage unbalance. And as we saw earlier, that voltage unbalance have the effect of increasing the current that is flowing through the system, and thus the heat that is dissipated in our electric motor. So how we do it is that once you have the motor connected like this, okay, you can test between, once you have this circuit breaker open, okay, your contactor closed, or you can come to the contactor end, because basically all of these two, they are closed in the MCC. Then from here to here, they are the cable supplying from here that runs from the MCC to the feed where we have the electric motor. So these ones are longer. These are very short runs. Okay, so we can do our test here even when the contactor is open. Okay, so we can run our test here. So when you run your low resistance test between line 1, okay, between line 1 and line 2, what you'll be doing, if assuming we have a star connection, that is, you are testing the resistance of this conductor, okay, through one winding in the stator coil, okay, and then through another winding, that is the second phase winding, then this yellow conductor to this point. Are we getting it? So which means that whichever point, if it is line 1, line 2, we take, line 2, line 3 we take, or line 2, line 1, line 3, and line 2, line 3 we take, you'll see that since we are looking at the same length of cable, the same resistances, that is the same winding, that two winding in each readings, okay, we expect that the resistance reading should be the same. Are we getting it? So again, we look at the unbalance here. Remember, we also look at the average, subtract each of these resistances from the average, the maximum deviation, as we said earlier, when we are looking at the voltage unbalance, we divide it with this average, okay, to give us the percentage unbalance. Are we getting it? So we're also looking at the same level between 0.5 and 2.5 is okay. But once it is higher than, it means that something is wrong. Okay, and that could mean that either any of these lines, they have high resistance connections, or within the electric motor itself, the windings may be shorted, or it has high resistance connection at their various connection points, either at the terminal block or within the windings where we solder the coils or the windings together. That could be the reason why we have this unbalance. So you need to check to ascertain which area in the circuitry is actually causing this unbalance. Remember, we tested from here to, we started the test at the MCC. So what will happen is that you can disconnect, go to the motor in the field, disconnect these three terminals, test the winding resistances. Okay, so if the winding, the resistance unbalance is not up to what you have, it means that the unbalance is generated along, or is created along these lines. So it could be that we have joints on these cables that are already failing, that are not properly made. Okay, so those joints, we can go and refix those joints so that we can improve or reduce the resistances of those joints. But if the unbalance is coming from within the electric motor, we need to check further, can do the winding inductance test to ascertain the level of unbalance in the inductance. Remember, the inductance will give us a better value than the resistance, low resistance meter, simply because the inductance in relationship with the resistance have a linear relationship or a direct relationship with the number of turns. Are we getting it? Why the inductance have an exponential relationship, n square. Okay, so that will give us a better idea of what is happening within the power circuit. Okay, so that is how we check the power circuit, but of course we will not neglect this part too. We will check to see if we have any high resistance points on any of these parts. And of course, we will also check the integrity or the reliability of the control system to see that it will also function as we intended it to function. So the air gap, as we talked earlier, we use the MTR 105 mega to test the rotor influence, okay, on the stator magnetic field. So the stator itself, like we also said earlier, we have the windings, okay, so we can do the low resistance tests on each of these windings, or we can do the inductance tests. Are we getting it? To see if there are any unbalance. Okay, remember, unbalance in the resistance will affect the voltage, can also introduce voltage unbalance that will eventually affect the operations of the electric motor. So that is what we will do. You can check out our training on resistance tests and also low resistance winding resistance tests, okay, on electric motor in our earlier section. So the MTRO2 can do it. So you see the milliohm selection. You can turn this your selector switch to the milliohm, connect your probe appropriately, then you can test, okay, and do your calculations to see if we have any resistance on balance. Okay, in the electric motor system, we have just looked at the electrical system reliability. Okay, so we want to look at the mechanical system reliability. Now, remember in the electric motor system, we looked at the input power to the electric motor. So now I want to look at the electric motor and the load that is attached to the electric motor. Okay, so like we said earlier, the load could either be pump, fans, compressors, and what have you. And between the electric motor and the load, we have what is called the coupling. That is the means with which the rotating mechanical energy is transferred to the load. Are we getting it? So we are going to look at the electric motor now and the load. Okay, because as we saw earlier, the electric motor also have some mechanical components that can affect the operations or the reliability of the electric motor and thus the electric motor system. So components like the bearing, okay, which actually help to ease the rotation of the rotor within the stator of the electric motor. So that component have a way of affecting the operations of the electric motor if it is bad. Then the rotor itself, remember, it is expected that it will be rotating constantly. We also see some of the things that can affect it, like unbalance, that will affect the operations of the electric motor mechanically and thus the entire electric motor system. So one of the most notable means of looking at the mechanical integrity of the electric motor system is vibration measurement and analysis. Okay, so we know that as the electric motor is working, its component parts, they usually vibrate. Now, when we say vibration, we mean the to and fro movement of this component about a main position. That is the molecules of these components about a main position. Okay, so this vibration, we have what is called the normal vibration when the equipment is operating normally, and then we have what is called the abnormal vibration that is introduced by fault condition, that is caused by fault condition. Okay, so we have simple instruments like the handheld vibration meter that will be able to give us the overall vibration level of the electric motor and the pump. So if we take the vibration readings, okay, of the electric motor at the bearing housings or around the bearing housing, as we'll see later in three positions or orientation around the housings. Okay, so we'll be able to get the overall vibration reading with the vibration meter. So when we are trending this overall vibration reading, as the vibration of the equipment, the total vibration is changing as it's increasing, we'll see it. And what is actually guiding this is the bathtub curve. Okay, so as the that parameter, that is the vibration level that we are looking at, as it's entering the PF area, that is point of potential failure and eventual failure area. Okay, you will see that we will see it with the handheld vibration meter that will give us the overall vibration level. So when it's entering that area, as the vibration is increasing, we can now use the vibration analyzer, okay, that will help us to analyze and determine the cause of that increased vibration. So this is the analyzer that, as you can see on the left of your screen, and this is the vibration meter. So these are instruments, okay, that we can use to monitor the vibration levels of the mechanical systems of our electric motor. So we are going to look at each of these instruments and how we could use them in the field, okay, on the electric motor. Now, like we said earlier, we have three orientations or positions that we can measure the vibration of the electric motor on each of the bearing housing, okay, or points. So now if you look at the motor itself, on this housing we can, since we have two bearings, okay, one on the drive end and the other at the non-drive end. So the one at the drive end is called the inboard bearing. The one at the drive end is called the inboard bearing, and the one at the non-drive end is called the outboard bearing. So the three positions are the vertical position, okay, that is the position that is at right angle, vertical right angle to the bearing on the housing. Then we have the horizontal position, as you can see on your screen here, okay. So if you look at this diagram, this point where you have the pointer is the vertical position, and here, okay, let's say here, because this is the cover, the fan cover, okay, so we will not get much information here. Let's say here, okay, that's the vertical position, and then here is the horizontal position, okay. So the position that is axial to the shaft, that is in the same axis with the shaft, is called the axial or axial direction. So we can look for any any part of the motor that we can take such reading axially, okay, and that will give us a reflection of what is happening around the bearing. So on the motor we have basically three measurement position and three measurement on the outboard and three measurement position in the inboard. That is what is stated here: motor outboard vertical, motor outboard horizontal, motor outboard axial or axial, okay. Then on the inboard, definitely, you know, we can only take the vibration reading when the equipment is working, okay. So for safety purpose, it may not be feasible to take the axial reading around the inboard end because of the shaft that is rotating and it may be covered, but we can take the horizontal and vertical vibration reading. Then on the pump end, the same thing too. We have the inboard, that is the part that is attached to the coupling, and then we have the outboard, okay, that is the part outside on the other part, on the other side of the shaft. Are we getting it? So those are the measurement points, okay, that we can take our vibration reading, which means that each time we go out to carry out vibration on a system like this, we have roughly 5 points here, 5 points here, that is 10, but ideally it is supposed to be 12, I mean to say 6 on each. So if it is possible, of course, because there are information that the axial vibration will give us. Are we getting it? So if it is possible, we should take the axial vibration reading also, okay. So all of these vibration information that we get, what information, or the vibration reading that we get, what information about the health of the electric motor, about the reliability, or that is about the integrity of the electric motor, it will give to us, okay. It will make us know so that we'll be able to improve the reliability of the electric motor if need be. So as you go to measure like this one, you can see that he is taking on the vertical position on this electric motor. Okay, so if it is the handheld vibration analyzer you are using, it will give the handheld vibration meter that you are using. It will give you the overall vibration level. So the only thing that can do for you, as we stated earlier, is just to help you to know when the vibration is increasing. So once it's increasing, you know something is developing within the electric motor. Are we getting it? But the drawback is that before it will show up in that increase, it may have gone far into the PF region of your bathtub curve, and it may not be recoverable again. That is, you may have little or nothing to do, or you may not be able to bring the situation back to what is close or what is normal or close to normal. Are we getting it? But if you have the vibration analyzer, as it is developing in the incipient stage, okay, you may see it. Now look at this analyzer as is used in the field. So you see the waveform on the analyzer, okay, looks like something on the right. This is the waveform. So to the ordinary eye, this waveform does not make a lot of sense. It's just like the voltage and current waveform that we saw with the power quality analyzer the other time. So here we have the effect of other forcing function, okay, that is other harmonics that are superimposed with the vibration waveform of interest. Okay, that is what is causing all of this distortion. But even at this, if you look at it critically, you will see a pattern. Are you getting it? And this pattern, this increased vibration, if you also look critically, you will see that they are occurring at regular interval. That will give you a sense as to the fact that something is happening at these intervals. Okay, it could be in pattern, especially if you look at these intervals coincide with one-time RPM. Are we getting it? So that is the beauty. But what is actually causing this vibration? Like we did in the voltage waveform, we can do fast Fourier transformation on this vibration waveform. Okay, and that will be able to separate each of the vibration waveform that we have, okay, into their respective frequencies. And the beauty is that various fault conditions in the electric motor, on the electric motor and even on the pump, okay, they appear at different frequencies, as you can see, as we will see later. Okay, so if you look at the analyzer, this is the spectrum that is underneath the waveform. Okay, so with this, you'll be able to know what is actually causing that increase in vibration, or what is causing this impact that you are seeing on this waveform. Okay, so with the experience and the rest, you'll be able to ascertain the causes. One important thing that most vibration analysts fail to do, and asset managers fail to do also, is that they feel that when we have fault condition, you just bring your analyzer. The analyzer will be able to pinpoint what is actually causing the problem. It may be able to give you, okay, but you have a better understanding of what is happening if you have been taking your vibration reading, carrying out vibration analysis regularly before, so that as you take, when the equipment is good, you try to analyze the waveform, the spectrum, to identify each of the forcing functions, okay, in that electric motor on the spectrum. What I mean is this. Let's take the electric motor for example now, okay. We have the bearing. We know that the bearing, okay, let me start from the rotor. We have the rotor, okay. That rotor, since it is rotating, it contributes its own level of vibration into the overall vibration of the electric motor. Are we getting it? And on each end of the shaft of the rotor, we have bearings. And if we are looking at ball bearings, you see that these balls, as they are rotating within the bearing race, either both the inner and the outer bearing race, you will see that it is also introducing some level of vibration. Okay, so if we are able to identify the frequencies at which the vibration that is caused by the rotor, the one that is caused by the bearing, okay, then on the pump side, the one that is caused by the bearing at both ends, then the one that is caused by the impeller itself, which will be the number of vanes that we have on the impeller times the speed of rotation. Okay, that is the fundamental frequency. So if we have 8 blades, okay, so the contribution of the impeller into the overall vibration will be seen at 8 times the speed or frequency, fundamental frequency of operations of that particular pump or electric motor, if it is not attached to a gearbox. Are we getting it? If you are able to identify all of these forcing functions, okay, when the equipment is working fine, when changes are happening, you'll be seeing them on each of the analysis that you carry out on each of the vibration measurement that you go out to the field to do. Okay, so as situations are developing negatively around the bearing, around the rotor, around the impeller, are we getting it? You'll be seeing them. Okay, and then if it goes beyond the level that you feel could be tolerated, then you can flag off the alarm so that what needed to be done to bring back the condition to normal should be done so that the vibration levels will reduce again. Okay, so when you carry out fast Fourier transformation on this, it will be able to separate the forcing function that are superimposed into this kind of waveform that we are seeing into their respective frequency. Okay, that is what you are seeing on this frequency spectrum. So you are seeing frequencies at different levels. So these ones, they are very high frequency events, okay, which may be contributed by bearings. Are we getting it? Which is determined by the number of ball pass frequency, the number of balls times the rotational speed of the machine. Okay, we have both for inner race and for outer race. So which part that is called, if there is a dent in the inner race, there is a particular frequency that you will see such problem. If there is a dent in the outer race, there is also a particular frequency that you see such problem. If the bearing is cocked on the rotor or is loosed on the rotor, okay, all of this, you will see all of this information on different frequencies, okay, of the spectrum. So like we said before, as you carry out the fast Fourier transformation, you have something like this. Okay, so 1 times the fundamental frequency, okay, 1 times RPM or 2 times RPM, we are seeing the peak. Then at higher frequencies, 10 to 20 times the fundamental frequencies, we are seeing different peaks. Are we getting it? So what are the things that are contributing all of these peaks, or what are the forcing function, okay, that are contributing at these different frequency levels? Should be able to identify all of this. So when you're able to do it, then you will know, assuming this frequency now is a ball pass, assuming we have say 18 balls in the frequency assumption, then assuming this is a ball pass frequency now, which means that if this vibration level, or this gives you the magnitude of vibration as against the frequency order, okay, the number of harmonics, okay. So if it goes beyond the tolerable limit, then you will know that the bearing is actually getting bad. Okay, so this is the fast Fourier transformation. So like we said earlier, specific peaks, okay, as you can see on the spectrum, they correspond to specific machine faults, okay, and they are all related to the speed of the machine. That is the beauty of vibration analysis. So they will help you to identify these problems, and you're able to nip it at the bud before it will affect the integrity or the reliability of the electric motor system. So as we see here, imbalance. Okay, as you see here, imbalance, they will typically appear at 1 times RPM. So you see a peak like this. If it is 1 times RPM, that is as a result of imbalance. So imbalance, as we know, is when the center of mass, okay, does not coincide with the center of rotation or the center of gravity of the rotor. Okay, so that would mean that we have imbalance on the rotor, and that will definitely increase the vibration of the electric motor. So that vibration, we will see them at 1 times, we'll see the peak at 1 times RPM once you have carried out your fast Fourier transformation, that is in its frequency spectrum. So if it is fan that is driven, the same thing. If the imbalance is on the fan, you also see it at 1 times RPM. So misalignment too, as you can see, you see it at the 1 or 2 times the turning speed. Okay, so misalignment is when the center of each of the shafts does not coincide with the center of rotation of the shaft. So that is misalignment. So we have angular and offset misalignment. Okay, so the one on the left is the offset misalignment, and angular misalignment is on the right. So in most cases, you will not see just one type of misalignment. You see a combination of misalignment, both angular and offset. So it makes the situation to be complex, as you can see. So you see that we have an angular and offset, okay, misalignment. This is what is common on in real life. Are we getting it? So this kind of misalignment, if it is in the system, you will see that in addition to the load, the motor will need to overcome that misalignment force, okay, around that coupling. So that misalignment force and the load that we are driving will mean that we will need more requirement on the electric motor system, which means that we will be overloading. We will giving the electric motor system or the electric motor itself more load than what we installed it for, because of that misalignment. And all of these increase in loading will affect the entire system. Remember, it will affect the heating of the motor, it will increase the load current, heating of the motor, and heating of all the electrical components, cabling and what have you, on the line to the point of input. Okay, So this misalignment, we can see it on the spectrum at 1 times or 2 times turning speed. So peaks at those two positions will tell us, but basically 2 times turning speed, okay, will show us the misalignment, and especially if we have that peak also on the axial direction. Are we getting it? That is a clear sign of misalignment. The looseness, when you have looseness, okay, you will see it at multiple peaks. There's multiple frequencies, the peaks at multiple frequencies. So when you have different and so many peaks, okay, on the spectrum, that clearly shows you that what you are looking at is looseness. So this could be taken care of by just tightening the hold down bolts and whatever bolts that is holding whatever part of the equipment. Are we getting it? So that's looseness. Then higher frequencies will give us idea about what is happening around the bearing. Remember, we talked about the ball pass frequencies, which is the number of balls times the RPM of the machine. Okay, so since we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 balls on this bearing, okay, so it means that information about this bearing will be seen around 11 times RPM, that is 11 times fundamental frequency. So which is around this area, okay, give us the bearing. Remember we said the inner rays and the outer rays, okay, actually you will see them at different frequency levels also, but close around that 11 times RPM. Okay, so we can also see jar burst frequencies at those higher order harmonics, okay, or higher order frequencies. Okay, so jar burst vibration, I mean to say, you see them at the higher order frequencies. Are we getting it? Which is notably around the jar mesh frequency areas. Okay, there is number of teeth multiplied by number of teeth of this multiplied by the number of teeth of the other. That is the number of teeth of the meshing jars. Are we getting it? So if one has 10 and the other have 5, the meshing frequency is 10 times 5, which is 50. So vibrations, you will see them around those 50 and above. Okay, so the vibration analysis will help us to pinpoint the cause of the increase in vibration. So another area that we need to look at again is the bearing. Remember, the bearing on the motor and the bearing on your load, that your driven equipment, they need to be lubricated. Okay, so how much lubrication is enough while lubricating? Let's take for example now, this electric motor that you are seeing. So you see the greasing nipple, okay, so this is where you attach this greasing gun to. Okay, this is you put the grease here and then attach to the greasing gun, and then you pump the grease into the bearing through the nipple. So how much of such grease is enough? When do you determine when to stop greasing each of these bearings? Okay, you see one at the non-drive end and the other at the drive end. Okay, so usually the normal practice, or what we used to practice in the field, is that when we go to grease with our greasing gun, okay, when we connect it to this greasing nipple, we start pumping the grease into the bearing housing. And as you are doing that, when the housing is filled, the excess grease will be coming out. Since you are pressuring from up, okay, it is since you are pressuring from up, all the old grease that you have here before will force through. Since you open this drain, will force out of the bearing housing. Okay, so normally what maintenance personnel they do, as the grease, they will be looking at the grease as it's coming out. Okay, so they stop when the neat or the clean grease starts coming out. So then they will presume that they have greased the bearing enough. But oftentimes, you will discover that after greasing, the bearing will heat up. Why is it heating up? It is because we have ended up over greasing the bearing. So how do we know when to actually stop greasing? Though experience may tell us, but that experience can also fail us. Okay, so if we use the ultrasonic greasing, as we are listening to it or viewing the ultrasonic signals directly, we will see the right point when the grease on it is enough. That is when the vibration or the ultrasound has reduced. Okay, so that will now introduce us to the ultrasonic greasing. What is ultrasonic greasing? Remember, ultrasound are sounds that occur at very high frequency above the hearing range of humans. Okay, so those are ultrasonic signals. Are we getting it? So though we cannot hear those ultrasonic signals, but there are equipment that will help us to either listen to ultrasonic signals or view ultrasonic signals. So if we attach this kind of instrument, okay, onto our greasing gun, or we use them in conjunction with our greasing equipment or instrument, as we are greasing, okay, we'll be listening to this or viewing the ultrasound signal, which is also like the waveform. So the dry bearing with dry grease, they always give very high ultrasonic signal. Okay, then as you grease it, that noise or that signal will be reducing. So once you see that sharp reduction, that will be a point to actually stop greasing the bearing. So what I've just explained, we will see it much later. Okay, so this is the effect of not knowing when to stop. You see, it affects, because since you don't know when to stop, and at times you may be expecting to come out from the drain nipple, not knowing that all these, they are going straight into the windings. As clearly shown, you see that this will close the air gap, prevent the rotor from running, subject the motor to lock rotor current that may eventually result to burnout of the windings. Okay, and then once these bearings, they are over greased, you will see that it will now have more than normal stress to overcome while it is turning, and that will generate heat within the bearing and the bearing housing. Okay, and that can affect the reliability of the bearing itself, and of course the integrity of the motor and the entire motor system. Okay, so this is how you deploy the ultrasonic measurement device. This is the one you look at the ultrasound level, the decibel level. Okay, you look at the decibel level as you are greasing. This is the greasing gun. As the technician is applying the grease, he is viewing the ultrasonic signal, the level. So the moment when the signal, the level comes down, okay, that becomes the right greasing point to stop. Are we getting it? Then on the right, he is viewing the waveform, okay, which is actually more reliable because you'll be looking at the waveform as we'll see later. Then when the waveform drops to a lower level, then you know that is the right time to stop greasing the electric motor. So this is what we are explaining. So this is the ultrasonic signal. You see that on the dry bearing or the bearing with a low grease is very high. Okay, so as you are applying the grease, pumping the grease into the bearing housing, it will come to a point when the signal will drop. So this is the point to stop greasing, because when you continue, you see that the vibration level, now you have over greased. Vibration level, the ultrasonic level will go up again. Are you getting? This is the area where you start causing overheat, okay, or heating up of the bearing. Okay, so we do not want that. So once it comes down, we see that it's a little bit steady down, then we can stop greasing. That is the optimal point, okay, or the point to stop. So you see that the ultrasonic greasing helps us to know precisely when to stop. So if you have not been deploying it in your system, okay, you are encouraged to actually deploy it in your system, apart from the fact that it will help you to save grease, okay, save some cost on grease. You'll see that it will help to improve the integrity of the bearing and the reliability of the bearing, and thus the reliability of the electric motor system. So the next technology that we are going to look at is the infrared thermography. Okay, this is another technology that will help us to ensure the reliability of the electric motor system. Remember, from the input of the power supply, okay, to our feeder to our electric motor, you will see that all of these lines, they are made up of conductors, okay, and these conductors, they have some levels of resistances, and even the windings of the electric motor itself, they have some level of resistances, which means that as current is flowing through all of these, okay, because of that resistance from I square R, there is bound to be some heat up on this okay, on these conductors, and the heat up will be highest at the point where we have higher resistances. Are we getting it? So the infrared thermography, since this heat is given off in the form of infrared energy, you can check out our training on infrared thermography. Okay, so since this heat is given off in form of infrared energy, though they are not visible to the ordinary eye, but we have instruments or equipment that will help us to look at this energy, infrared energy, as it's coming out from those heated body, and that is the infrared camera, as you can see. Okay, so this infrared energy that is coming out will now be converted into a visible form that will now make sense to us. Okay, so like we said, since we have resistances on the line, heat will be generated during normal operation because current will flow through. So we have the normal heating level. On the thermogram, we have what is normal for all of these components, including the electric motor, as we will see later. So any deviation from what is normal, as we view on the thermogram, as you can see here, Okay, you can attest to the fact that these are not the same. There's something happening here. Okay, so if there's any deviation, that will tell us that something is building, and it is definitely because of a resistance buildup around that area. So what can cause such resistance buildup is what we need to check. And remember, those resistance buildup can introduce unbalance in the system, and unbalance can increase the heating of the system and reduce the integrity and reliability of our electric motor system. Okay, so we want to use this to detect hot spots in the electrical system. Hot spot is synonymous with spots or points of higher resistance that can introduce resistance imbalance into the system. Are we getting it? Into our electric motor system, which we know is detrimental to the operations of our electric motor. Okay, so the electric motor itself, as you can see on the right, okay, it has its own normal thermogram. Remember, we have windings around the stator. So these windings, they are made up of resistive materials or conductors, and as current is flowing through them, heat is generated, and that heat is conducted onto the frame of the electric motor. Okay, so that heat that is conducted onto the frame of the electric motor is given off in form of the infrared, which we are seeing here. So this is a normal thermogram. You see that the middle of the motor will be hotter. Are we getting it? Because the windings, they are concentrated in the middle of the motor. So remember, as we saw earlier, at the non-drive end, we have fan that is covered by this shroud or cover, fan cover. Okay, so you can see the cooling effect of the fan. So if the fan is not working and the motor is on, this cooling effect will not be there. You will not see this gradient from cool to high. Everything will be at the same temperature. So that will tell you that your fan has failed. Then if you have those fins, remember we said we don't need them to be blocked. If you have them blocked, okay, you will not also see this thermogram. Then if you come to the front, remember we have bearing around this front housing. So that bearing, because of the frictional force around the bearing, heat is always generated around the bearing when it is working, and that heat is given off onto the bearing housing. Are we getting it? So that heat, you see that heat around the bearing housing. So this is a normal thermogram, but this heat around the housing, we have the normal level. If it goes beyond what is normal, okay, you will know that there is a problem developing in that area. So that means that we need to carry out the quantitative analysis, okay, which means that we need to do the delta T analysis. So if here, maybe here now is what we have as the highest temperature on this thermogram. Say here is about 48 degrees Celsius. And then we have our ambient temperature to say 32. Are we getting? So our delta T in this case, okay, will be around 16 degrees Celsius. So 16 degrees Celsius delta T is okay. But anything above 40 degrees Celsius means that something bad is already happening on any equipment, okay, and especially the electric motor system. Okay, so on the left, you see what we see with our ordinary eye. This is the visual image, and this is the thermogram of this visual image. So what we see on the motor is a normal thermogram because we see the cooling effect of the fan. We see the hottest spot on the electric motor, and then this is the jar bus. Okay, we are also seeing what is happening around the jar bus. Okay, I will know the reason why, because we have meshing jars, a lot of friction. Okay, so it's expected that it should heat up, but it also have a normal heating level. So with the infrared thermography, we're able to ascertain the reliability or able to improve or we'll see what is happening from the power system and even the mechanical system of the electric motor system. We can also look at the pumps too. You can see the driven load. It has its own normal thermogram, okay, what we are used to seeing. So if there are deviations, you also see them around the bearing housings. If they fault with the impellers, you also see all of these deviations. So this infrared thermography in conjunction with other technology will definitely give us what is happening around the electric motor. So if you look here too, you see the normal thermogram of the electric motor itself. Okay. Then on this, you see from the circuit breaker, you see this clearly shows that we have loose connection here that can result to increased resistance that can result to voltage imbalance in our system. Okay, so if the system is overloaded, you see that there won't be any temperature gradient. The three-phase will be overheated. You see the hot, high temperature. So you see with the infrared camera or infrared thermography or the infrared, this technology, we'll be able to look at the entire electric motor system from the power supply through the feeder lines, all the components of the feeder lines, the electric motor itself, and of course the load we have on the electric motor, the compressor, the pump, and the fans, and what have you. Okay, so this is another technology that will help us to improve the reliability of our electric motor system. So all of these put together will definitely help us to ensure the reliability of our electric motor system. Okay, so which means that we consider the reliability of the electrical system and the mechanical system of the electric motor system. Remember, we identified the 6 fault zones and what to do to ascertain that those fault zones will not affect the reliability of our electric motor systems. Okay. Then on the mechanical part, we identified 3 technologies. The vibration analysis that will help us to look at the electric motor and the load, pump, compressors, and fans. Okay, the integrity. Then the ensuring the reliability of the rotating component, which is the bearings. Okay, ultrasonic greasing will help us to know how to apply the right grease